Good afternoon, guys. I have discussion A for you. We're discussing today smart sensor in knee replacements. Okay, so that is today's discussion A. Please join me. And remember, folks, that if you have comments during the show, uh, things that you want to discuss after the show, leave them in the comments below for me, and we will see what we can do about doing a show on your question or your answer or things of that nature. Okay, so here we go. Smart sensors in knee replacements. What researchers did. A team of engineers at Binghamton University, led by Professor Shahzad Sherry, 2010, was spent nearly a decade pushing the boundaries of what a knee implant can do. Their work brings us closer to a future where a replacement knee doesn't just sit in the body, it communicates. These researchers have developed miniature implantable sensors capable of measuring the mechanical loads inside an artificial knee joint in real time. This is a major leap because current implants provide no internal feedback at all. Surgeons and patients are essentially flying blind. Once the implant is in place, how the sensors work. The innovation hinges on a clever pairing of tubi, trib, turbo electronic and piezoelectronic transductors materials that generate electrical charge when rubbed or pressed or vibrated. Every step you take becomes a tiny power source instead of relying on a battery, which would eventually die and require replacement. The implant harvests energy from the natural movement of the knee. Even better, the same materials that generate power also function as load sensors, meaning they can detect how much force the joint is experiencing during daily activities. The dual purpose design keeps the device compact, efficient, and self sustaining. Why it matters. Knee replacements is Knee replacement is one of the most common surgeries in the United States, with nearly 800,000 procedures performed each year. Yet, 1 in 5 patients eventually develops complications such as loosening or imbalance problems that often go unnoticed until they become severe enough to require revision surgery. The second surgery, these second surgeries are more complex, more expensive, and harder on the patient. Smart sensors could change that equation entirely by providing early, non-invasive insight into how the implant is performing. Clinicians could intervene sooner, adjusting physical therapy, modifying activity levels, or addressing mechanical issue before they escalate. Validation, next steps, and limitations. Validation so far. The research team has already tested the sensor in a sophisticated joint simulator capable of reproducing the knee's full range of motion. 6 degrees of freedom. They've also published multiple peer-reviewed studies exploring the best materials, geometrics, and energy harvesting strategies to minimize sensitivity and durability. Remaining engineering steps. Before these sensors can be implanted in humans, they must be fully sealed to protect the electronics from bodily fluids, proven biocompatible over years of use, and validated in cadaveric models to ensure they behave accurately in real anatomical environments. Only then can clinical trials begin. Practical hurdles. Even with strong engineering, real-world adoption requires solving several challenges, ensuring wireless signals can reliably pass through tissue, and integrating the sensors into existing implant designs without compromising structural integrity. Navigating regulatory pathways for implantable medical devices, keeping manufacturing costs reasonable so the technology is accessible. These hurdles are solvable, but they will shape the timeline, patient impact, and timeline potential benefits. Imagine pinpointing your phone at your knee and instantly seeing how your implant is performing, how much stress it's under, whether your gait is improving, or whether certain activities are putting you at risk. This kind of personalized activity specific feedback could transform recovery for clinicians. Continuous data could reveal subtle patterns that are invisible during occasional office visits for patients. It could mean fewer complications, fewer revisions, surgeries, and a more confident return to daily life. When might it appear clinically? Although the progress is exciting, the technology is still in the preclinical phase. After device sealing and converting testing, the path to human trials, regulatory approval, and commercial availability typically spans several years. Still, the trajectory is clear. Smart implants are coming, and they promise to reshape orthotic care. Smart knee implants are edging closer to everyday clinical reality, and the headline you shared captures exactly why. Engineers are now demonstrating self powered embedded sensors that can track joint stress in real time without relying on batteries. Once sounded like science fiction, and an implant quietly monitors its own health from inside the body, is now emerging from labs with nothing, with enough maturity to imagine in real clinical workflows. what's actually happening. The research, especially the researchers, especially the long running team led by Professor Shahzad Sherry Tuflagan at Birmingham University, have spent years refining miniature ultra durable sensors that can be embedded directly into the knee implant. These devices sit at the interface where the metal and plastic components meet, measuring the force, the joint, measuring forces, the joint experience during walking, climbing stairs, or even standing up from a chair. The breakthrough is that these sensors power themselves. They harvest energy from the patient's own movement using two mechanisms: piezo electronic materials, which generate electrical charge when it compressed. Tribo electronic uh, materials, which generate charge when surfaces rub or separate. Because the same materials that create energy also respond to mechanical load, the design becomes eloquently compact. No batteries to replace, no wires to route, no bulky modules to implant. Every step becomes both a data point and a power source. Why this matters for patients. The stakes are high. Nearly 800,000 knee replacements occur annually in the US, and 1 in 5 patients eventually develops complications such as losing instability, or even unaware. These problems often progress silently until implant fails, leading to painful revision surgeries that are harder on the body and more expensive for families and health systems. A self-powered sensor changes that equation. It can detect abnormal loading near clinicians could adjust physical therapy, gait training, or activity levels to prevent damage. Data could help distinguish between Patients might one day open an app and see how their implant is performing, turning recovery into a guided confidence building process rather than a guessing game. For older adults, especially those balancing mobility, independence, and chronic conditions, this kind of insight could be transformative. The technology is no longer theoretical. Multiple research groups have demonstrated proof of concept devices that harvest enough energy for step to power low low duty cycle sensing and wireless data. Transmission, these prototypes have been tested in joint simulators that mimic years of walking, mechanical knee rigidity that replace real world forces, battery free prototypes that successfully transmit data using only harvested mechanical energy. The remaining challenges are ones you'd expect for any implantable device: long-term stealing to protect electronics from bodily fluids. Okay, guys, that is your A for now. I will see everybody for B shortly. Give me a bit for that, and I will be back on with B for y'all. For now, Gator Wellness. Take care, folks.